So let's get started. I want to talk about interior layers mostly today. And the idea in general is that the additional step, as opposed to just boundary layers, is to locate where an interior layer might be. And so in particular, if we have some ODE and we know that there's an interior layer somewhere, we can use information from the ODE to determine where our boundary layer has, where our interior layer has to be. And last class, we reasoned this out for a particular example, okay? Epsilon y prime prime is equal to y prime minus y, living on x is 0 to 1, and y of 0 is equal to 1, y of 1 is equal to minus 1. We call this boundary value problem star. And so if we want to determine where the inner layer is, right, we essentially reasoned out that it can't be on the left, okay? Okay, because we would need y prime prime greater than 0, y prime is less than 0, and y is greater than 0, and y is less than 0. And this would imply that the left-hand side of star is greater than 0, and the right-hand side is less than 0, somewhere in that region, okay? And similar logic excludes right boundary layer, okay? And so for interior layer matching, we're going to use the change of coordinates x bar equals x minus x0 over epsilon to the alpha, okay? Where x0 is some value between the boundaries. And then we're going to have two outer regions now, where x is from 0 to x0, and from x0 up to 1, okay? And we'll recall that our outer solution, basically for where epsilon equals 0, that's relevant here is going to be y0 is equal to x plus a. Now, you don't have to keep this constant the same, and you won't keep it the same in these two different outer regions, okay? And so that's going to allow you to break up your outer solution and satisfy both boundary conditions, okay? So allowing for different A in either outer region basically satisfies our boundary conditions, okay? So we'll get back to that later, but for now, let's focus on the interior layer, okay? So for the interior layer, as we wrote down before, we have this x bar here. This is going to be our change of coordinates. If I plug that in, I end up with epsilon to the 1 minus 2 alpha y bar prime prime equals epsilon to the minus alpha y bar prime minus y bar. Okay. So in this case, the way I get the distinguishing limit, I could take alpha equals 0, but then I'd be back to square 1. That would match up these two terms. Okay. If I just wanted to match this term and this term, I could take alpha equals a half, but then I would just have one term here that would actually be my leading order term, epsilon to the minus 1 half. So if I match this term and this term, right, then they'll be leading order, okay? And I'll, for the time being, ignore this, this additional term over here. So the distinguishing limit in this case is going to be alpha equals 1. And I can also expand my interior solution, okay, according to some regular perturbation expansion. Y0 bar x bar plus epsilon y bar 1 x bar, okay, and so on. Okay. Now, we could try some irregular expansion, but let's just start by trying regular perturbation expansion. Then this limit, right, I've matched these two terms here. So I can just write out the ODE in that case. And I get y0 prime prime, y0 bar prime prime, y0 bar prime, okay? I can integrate this equation and I get y0 prime is equal, bar prime is equal to 1/2 y0 prime plus a, okay? Now, this is a separable equation. We can use partial fractions, okay? I won't go through the details of the partial fractions, but you can see that, depending on what a is, you're either going to have, something like, sorry, it's y0 squared here. You're either going to have a polynomial here with no real roots, or you're going to have one with sort of opposite roots, and so depending on that, we're going to have 3 different types of solutions that we can get in this case. One's going to be the special case where a is 0, the other is where a is positive, the other is where a is negative. So let's just write out the 3 types of solutions, okay, using separability and sometimes use partial fractions, other times use trig identities, okay. Trig integrals, basically. And so one type of solution is going to be y0 bar equals b times 1 minus b e to the b x bar, 1 plus b e to the b x bar. Another type will be y0 bar is equal to b tan c minus b x bar over 2. And a third will be y0 bar equals 2 over c minus x bar. So that's that special case one. And essentially we have to check each solution for matching, okay? And only one of them is going to, because if I take the limit of this as x bar goes to 0, I can only get back 0 in this case. So that excludes 3, okay? If I take the limit of this as x bar goes to infinity, I have a periodic function, okay? So I can't do matching with that. So only 1 is going to work, okay? So 1 works for my matching conditions. I now just have to specify my coefficients in order to get everything to match up right. Okay, so as x bar goes to positive and negative infinity now, okay, this is what's going to allow me to sort of tune my function so that stuff matches correctly. So in this case, y0 is going to go to minus b as x bar goes to plus infinity, b as x bar goes to minus infinity. And now I have the freedom to specify b, okay? I still don't know what d is, but that's okay. I just have this free constant floating around now. And now I can go back to piecing together my inner and my outer solution, okay? So, so let's look at maybe the left domain one, and I'm going to just sort of draw a picture now. So what's happening here on the left picture, remember that over here, y is equal to 1 at x equals 0, okay? I have this x plus a, so that tells me that a is probably going to need to equal to 1 here, okay? There's going to be some value here that I hit, and I want that to be where y is equal to b in this case, or I guess negative b, right? So b is probably going to be, sorry, it's going to be positive b. So positive b in this case, okay? So this is where my inner solution is going to hit my outer solution. So this is going to be my y bar here, okay? So 0 is less than or equal to x is less than x0, okay? Y0 is equal to x plus a, right? Or x plus 1 in order to satisfy my boundary condition. Okay. And then on the other region, I'm going to have that y0 is equal to what? Well, we're going to come down here, right? Here's x equals 1. And I have my linear function here, but it needs to hit y of 1 equals minus 1. So that means that y0 needs to equal x minus 2 down here, okay? All right. So for free, by knowing that I need to chop this function in half and piece it together at the boundary conditions, okay, I have a restriction on what my inner solution can go to. It has this sort of odd symmetry to it. So that means that whatever this value is, it needs to be the negative of this value, okay? And the only way that can happen is if x0 occurs right at 1/2, okay? So that is going to place my interior layer, okay? So now I've resolved the value of x0, and I can also get the value of b in the process, okay? So on this right outer region, I have y0 is x minus 2, right? Because y of 1 is equal to minus 1, okay? And as I said, when we match, we end up with y0 bar at infinity needs to equal y0 of x0 plus, okay? And y0 bar at minus infinity needs to equal y0 of x0 minus. Okay? So this essentially means that minus b is equal to x0 minus 2. B is equal to x0 plus 1, okay? And I can solve this pair of linear algebraic equations, and I get b equals 3 halves, and x0 equals a half, okay? So I'm almost done resolving all the constants of my function, except the question is, what is this d variable here, or sorry, this d parameter here, okay? Now, because y0 is sort of going to cross y bar at x0, right, is going to have to cross right through 0, okay? That's going to be the additional thing that helps me specify this, right? So note, right, y0 bar at x0, that's going to have to cross right through here because of the symmetry of my function, right? So this is right at x0 equals a half. I have that y bar of x0 is equal to 0. Okay. So, and that's because y prime is less than 0, and y prime prime, right, has an inflection point there. Okay. And it switches sign. Okay. And so the ODE then requires that y equals 0. Okay. All right, well then that means that y bar at 0 is equal to 3 halves times 1 minus d, 1 plus d equals 0. The only way that can happen is if d equals 1, okay? Therefore, y bar is equal to 3 halves 1 minus e to the 3 x bar over 2 divided by 1 plus e to the 3 x bar over 2, okay? And our inner solution is then fully specified. Okay. Questions about this so far? All right. So we're almost done constructing an interior layer problem solution, okay? Let's just finish off with the composite expansion. And the composite expansion, right? We have to work it out for both sides, okay? Okay, so we'll do 0 to x0 first, right? So in this case, we have that y0 is equal to x plus 1, okay? And y bar of 0 is equal to 3 halves 1 minus e to the 3 x bar over 2, 1 plus e to the 3 x bar over 2. But in the limit as x bar goes to negative infinity, I'm just going to get that it's going to go to 3 halves as x bar goes to negative infinity. Okay. So that's going to be 3 halves, and that's going to be 3 halves as well. Okay. So I can subtract off that additional 3 halves. So we get that y is approximated by x plus 1 plus 3 halves times 1 minus e t of 3x bar over 2 divided by 1 plus the exponential of 3x bar over 2 minus 3 halves. Okay. And when we simplify that down, do that on the next page, we get that y is approximated by x plus 1 minus 3 divided by 1 plus e to the minus 3 times 2x minus 1 over 4 epsilon in this case. Okay. Okay. And similarly, okay, the composite on x0 to 1 is the same. Okay. So what you should find at the end is that you don't have any jump discontinuities, right? So remember that, you know, when we constructed this outer solution, okay, if you really wanted to write this down without the inner solution, you would end up with a jump discontinuity. You could use like a Heaviside function to write this down for just the outer solution. The role of the interior layer is to smooth out that Heaviside function so that you get a nice continuous transition between your outer solution. So at the end of the day, you should remove that, you know, jump discontinuity, and what should happen is that you have this sort of smooth function in between. So if I take the limit of, you know, on the other side of 1/2 here, right? When x is slightly greater than 1/2, I'm just going to have x minus 2, okay, in this case. But in order to get there, I didn't have to use a jump discontinuity, okay? And so what we should find is that y as a function of x, now this nice smooth function, you know, y is equal to -1 here, y is equal to 1 here, okay? And this transition here happens at x equals 5, okay? All right, and the smoothness of this is gonna, it's gonna become smoother and smoother as you take higher values of epsilon. But of course, you expect maybe your asymptotic expansion would break down. Okay, so that's interior layers. So just to sum up, right? You want to find the outer solutions, okay? You want to change variables to get inner layer equation. X bar equals x minus x0 divided by epsilon to the alpha. Now find distinguishing limits, okay, for alpha, and solve, okay, and then you'll generate matching and boundary condition equations to specify constants, and in particular x0, okay, and then lastly you'll make the composite C. Okay. All right. So really only one additional step for boundary layer problems. Okay. Any questions about this? All right. Okay. Corner layers. I think we can go through corner layers and then we'll be done for today. Let me talk about corner layer problems now. Okay. they're really not that different from interior layer problems. The main difference is that you're trying to smooth out the derivative rather than the function itself, okay? So sometimes rapid changes occur in the slope of y, but not y itself. Okay, so let's take a general differential equation, epsilon y prime prime plus x minus a half p of x y prime minus p of x y. Okay. And we're going to, okay, so we're gonna say this is equal to 0 here. X goes from 0 to 1. And let's actually specify specific boundary conditions. Okay. And we want that P of X is smooth and positive with P of 1/2 is equal to 1. Okay. So for example, P of X is equal to X plus a half, or P of X is equal to E to the 2X minus 1. Okay. And we'll note that in this case, the coefficient of y prime equals 0 right at x equals a half in this case. All right. So what I'll say is that there's going to be what's called a corner layer at x equals a half. Okay. And our outer expansion, or like expansion in our outer layer, we'll write as y as approximated by y0 plus epsilon y1, and so on. Okay. If we plug this in, we have a separable equation that we can solve. And in particular, I get that y0 equals a times x minus a half. Okay. So our outer solution, right? We have this free variable a, or sorry, this free parameter a that can specify our slope. It turns out for this problem, in order to get our boundary conditions satisfied, we need to take the slope to be different. So then when you come together at this interior layer, in particular, it's going to be a corner layer because you're going to get a jump in the slope. Okay. So in order to sort out our inner solution, we note that we're going to have what's called a corner layer. There's going to be no boundary layers in this problem, okay? Since at x equals 0, y prime prime is greater than 0, y prime is less than 0, and for some portion, y is less than 0, okay? So that means I'm going to have epsilon y prime prime is greater than 0, okay, which is greater than the negative of the rest of our equation, okay? So sort of following the same logic as before, okay? And similarly, can show there's no layer, inner layer at x equals 1, okay? All right. So I won't unpack that too much because we did it in the other problem. Okay. But you know, the arguments are similar. Okay. So therefore, we're going to have some interior layer. But not because of any jump discontinuity in the function. Okay. So x bar is equal to x minus x0 divided by epsilon to the alpha. And this is going to be our interior variable. Okay. Well, let's kind of collect what we have for now, right? We have our outer solution, and that's going to be using our boundary conditions. If I just go back to our boundary conditions here, right? Okay. I can figure out what these coefficients have to be, right? So I know that y of 0 in this case is equal to 2, and my boundary condition, the value of my function at my boundary is going to be a times minus 1/2. So that means that a equals minus 4, okay, on 0 to x0, okay. Y of 1 is going to equal 3, okay. So that's going to be equal to a over 2, right? Because I have 1 minus a half there. So this implies that a equals 6 on x0 to 1, okay? So my outer solution is resolved. I have y0 is equal to minus 4 x minus a half, 6 times x minus a half, okay? 0 up to x0. And x0 up to 1, okay? Now, this will only be plausible, okay, if x0 equals a half, right? So basically to rule out discontinuous outer solutions, okay? Essentially using the same arguments as before. You can say, well, let's assume that there's some discontinuous outer solution. In order to resolve that, I would need to have an inner solution that connected this jump discontinuity. But if I do that, I end up breaking some of the conditions of the ordinary differential equation, okay? So I break sort of the plausibility argument, okay? So the only possibility is that minus 4x0 minus a half is equal to 6x0 minus a half, okay? And if we solve this, we find that x0 is equal to a half, okay? So that means that our outer solution is continuous, okay, but non-differentiable, okay? And that's okay because now we have what's called a corner region, okay? And the procedure for the corner region, it's not too far from an interior layer, okay? We substitute our stretch coordinates in, right? We perform our appropriate expansions, right? And we figure out the distinguishing limit, and then we solve our leading order equation, okay? So if I sub in my stretched or inner coordinate, what I get is, and I'll call this dagger, I get epsilon to the 1 minus 2 alpha y bar prime prime plus x bar p times 1/2 plus epsilon to the alpha x bar y bar prime minus p of 1/2 plus epsilon to the alpha x bar y bar equals 0. Okay. Now I'm going to Taylor expand p to truncate out some of that. So I get p 1/2 plus epsilon to the alpha x bar p prime of 1/2, okay, and so on. So I basically get, because of my assumption at the outset, I get 1 plus order epsilon to the alpha term. Okay. So in order to balance my terms, right, I only have one term involving epsilon, or I only need two to leading order. These are just order 1 terms, right? So I get alpha equals 1/2, okay, from balancing all terms. Okay. Now we're going to take y bar is equal to this regular perturbation expansion. Okay. Y. Let me be a little more careful about this. Okay. Y bar I can write as y0 at x0, right? Whatever that is. Okay. Plus now, and I could take a regular perturbation expansion, but I'm going to take an arbitrary scaling of my first correction term. Okay. And you often don't have to do this in interior, just plain old interior layers. Okay. But for corner layers, sometimes you end up having to match the scaling of your stretch coordinates. Okay. So here our inner coordinates, right, are going to have a scaling of epsilon to the 1/2. That means when I differentiate that, okay, in order to balance the order 1 changes in the derivative that happen rapidly, I probably need to take my scaling of y bar 0 to match that, okay? It may not be that I can just take a scaling of epsilon to the 1 in order to make that work, okay? So that's why we're introducing an arbitrary scaling here, okay? And in this case, right, if we plug in x equals 1/2, right, to our leading order solution, we get that y0 of x0 is equal to 0, right? So this part's just going to be 0. So really, the only thing I need to worry about here is this leading order term, okay? My epsilon to the gamma is going to help match to the outer solution. Okay. So we're going to sub this into our differential equation, and we end up with y0 bar prime prime plus x bar y0 prime minus y0 prime is equal to 0. So x bar is going to just live on the reals, right? It can go from minus infinity to infinity because I'm in this stretch coordinate space now. Okay. What's happening here, if we take a step back, is that y looks like this. Okay. I'm going to have my left outer solution go like this, my right outer solution go like this, and then in between here is my corner layer. And if I sort of zoom in on that, what I should get is something that rounds that corner off appropriately so it's not sharp. Okay, so this is what I'm going to want to see in y bar 0, some kind of function that looks like that. And it's going to have a different slope here than it has here. Yeah, and I guess, you know, we need this epsilon to the gamma term. Okay. All right. So that's what we should be anticipating. Okay. So now note that y0 bar equals x bar is a solution to this. Okay. So we can use what's called a reduction of order method. Okay. We have that solution. Okay. And yeah, I can send you more details on reduction of order method if you want. The other terms in the solution then are going to be given by b times e to the x bar squared over 2 plus x bar integral from 0 to x bar e to the minus s squared over 2 ds. Okay. So oftentimes with these, you know, nonlinear or variable coefficient interior layer problems, yeah, you have to pull out a number of different methods from ordinary differential equations. So I can send you some supplementary materials on that method. Okay, so the point is, though, it's assuming that we can get some sort of solution like this, we hope that it has some free coefficients. Okay, it does. In this case, we have 2 free coefficients, but we already have our x0 constraint, so that's not a free coefficient anymore. Okay. But if we want to now look at matching in this case, we're going to match using intermediate scaling as we have in the past, and the idea is just to take some intermediate variable x theta, where we have x minus a half over epsilon to the kappa, and kappa is going to be some scaling between 0 and a half. Okay, so as we're leaving our interior layer and entering our outer layer, there's some intermediate scaling that bridges in between those, and that's where we want to look in order to try and match using our free constant. Okay. So so in this case, if we take y, we have that y is approximated by 4 epsilon to the kappa x eta, 6 epsilon to the kappa x eta for x eta less than 0 and for x eta greater than 0. Okay. And also, since the integral from 0 to infinity of e to the minus s squared over 2 ds is equal to the square root of pi over 2. We have that our inner solution, y bar, can be approximated as epsilon to the gamma plus kappa minus a half x eta times a minus beta square root of pi over 2 for x eta less than 0, epsilon to the gamma plus kappa minus a half x eta a plus beta square root of pi over 2. Okay, so that's just taking us out of the inner layer means, yes, taking the limit of large x eta in this case. Okay. So now to match y bar and y, we need, in particular, that gamma is equal to a half in order that we get the right scaling to match the alpha equals a half that we took before. So that means that a minus beta square root of pi over 2 is equal to minus 4. A plus beta square root of pi over 2 is equal to positive 6. Okay. So in this case, right, if we're to differentiate inside of the layer, right, we're going to get this extra factor of minus 1/2 coming out that should, so gamma essentially needs to cancel this 1/2 in order for the scalings to be right here. Okay. And then all we have to do is match essentially the coefficient that I get here to the coefficient I get here, the coefficient I get here to the coefficient that I get here. Okay. So I have this linear algebraic equation now that I can solve. A equals 1, B equals 5 square root of 2 over pi. Okay. And that's the coefficients of our inner corner layer solution now. Okay. So the composite expansion, just to wrap up, is going to be, for let's say x goes from 0 to a half, we'll have y is approximately minus 4 x minus a half. That's our outer solution. Epsilon to the 1/2 x bar plus 5 square root of 2 over pi e to the minus x bar squared over 2 plus x bar integral from 0 to x bar e to the minus s squared over 2 ds, okay, plus 4 epsilon to the kappa x eta, okay. So we can approximate this as x minus a half times 1 plus 5 times the error function x minus a half divided by square root of 2 epsilon, and then plus 5 square root of 2 epsilon over pi e to the minus 2x minus 1 squared over 8 epsilon. Okay. So again, we had a jump discontinuity in our derivative in the outer solution. If we differentiate this, we should no longer have a jump discontinuity because the corner layer solution is going to smooth that out. Okay. So this also works for the x goes from a half to 1. So typically you only need to satisfy the composite solution on the left, and it should extend to the right appropriately. Okay. So so just to sum up, what we find then is that we sort of draw x equals 0, x equals 1, and x equals a half here. Okay. We have this corner layer solution here. Okay. And it smooths out the jump in the derivative, okay, of the outer solution. Okay. So how do you deal with corner layers, right? Okay. You solve for the outer solution first, okay? And then use a plausibility argument to rule out boundary layer or a jump in interior layer. You rescale at the corner, solve the inner solution, specify constants, okay, with matching, okay, and then construct the composite. Okay. So for interior layers, for corner layers, for boundary layers, okay, the techniques are similar. There's a little bit more work involved for yeah, boundary and interior, interior and corner layers. But the ideas are fairly similar. Okay. So that brings us up to PDEs, which will start on Monday. Sorry, I went a little bit over. Are there any questions before we conclude for today? Okay. All right. Well, have a good weekend, and I'll see you on Monday.
Thank you.